At the end of a long journey, stars sometimes explode. When that happens, they produce a huge number of new atomic nuclei. Some of these nuclei live for very short times, just a fraction of a second, and then they decay away. They turn into new nuclei and new elements. Those decay products are the chemical elements we find in the cosmos today. To understand how these explosions work and what elements they make, we need to know the properties of these short-lived exotic nuclei. But how can we produce and study here on Earth something that lives for such a short time? All stars are hot, at least for Earth standards. But for star standards, there's a huge variety in their temperatures. Some stars, like our Sun, have central temperatures of only about 20 million degrees, which sounds high, but it is about 100 times cooler than, for example, the center of a more massive star that explodes as a supernova. The fuel for a star's energy comes from nuclear reactions. If the temperature is low, nuclear reactions are not very easy. But at high temperatures, oh my, things can get, well, explosive. Some of the nuclei produced in those stellar explosions live for very short times, just a fraction of a second. They play their part in the star's energy production and the production of new elements, and then they're gone. But what exactly is this part that they play? How much energy do they release? How do they interact with the other nuclei in the star? What do they turn into when they decay? So many questions. Since we can't travel inside a supernova, we can only answer these questions if we could somehow make these rare nuclei in the lab and study them. But how do scientists create and study exotic or rare isotopes in the lab? Well, the recipe is simple, although the implementation may be a bit harder. Ingredients: stable atoms that can be found on Earth, a particle accelerator, a target, a powerful filter, and radiation measurement devices. In fact, it involves different stages. Number 1, ionization. Atoms in their natural form are neutral. They have no electric charge. First order of business is to kick out some of the atom's electrons. This part is called ionization and leaves behind some nice positive ions that we can push around easily. How? With big magnets and electric fields. Number 2, acceleration. We take our positive ions and put them in an accelerator. The accelerator can be circular, like a cyclotron, or it can be linear. No matter what we use, the end point is a beam of particles that goes pretty fast. How fast? About half the speed of light. This means the particles go around the Earth 4 times in 1 second. Number 3, fragmentation. As exciting as this might sound, these nuclei are not what we're interested in. To get to the more rare ones, we need to smash the fast-moving beam into a target. And boom! Our initial nuclei break into pieces and hundreds of new nuclei can be produced. It's pretty cool, but now we run into another problem. How do we separate the one we're interested in out of this mess? Number 4, separation. The next step requires a powerful filter to get rid of all the unwanted isotopes and select the one we want to study. And number 5, detection. Finally, once the beam of rare isotopes is ready, then it gets delivered to the experimental station to study it. This nice, well-tested recipe, like my grandma's cookies, has worked for several decades. So why do we not yet know everything there is to know about rare isotopes or exploding stars for that matter? It is because the isotopes that are created in stars are so rare that even our most powerful accelerators cannot create most of them today. For this reason, we develop new accelerators that are more and more powerful, which means they can produce exactly those isotopes that are also created in the stars. I work at an accelerator laboratory which specializes in producing such rare isotopes, hence the name, Facility for Rare Isotope Beams, or FRIB. At its full power, FRIB is expected to produce more than 1,000 new isotopes that are present in stellar explosions. Then, all we have to do is deliver them to the experimental station and study their properties. At FRIB, the process of producing rare isotopes and delivering them to the experimental station takes a few billionths of a second. So we can basically watch the process of element creation that happens in stars live in the lab. Pretty cool, huh? With all the current and future rare isotope facilities around the world, these are really exciting times for rare isotope science and for learning about the stars. Stay tuned and check more recent developments about the cosmic origin of the elements in the next episode of Astronuclear Nibbles.